Hi everyone, let's start chapter 10, which is about verification and validation. On the course map, we have learned all the knowledge that we need to build a simulation model. So now we assume that we have a simulation model and we want to see how is the model. So in this chapter, chapter 10, we will learn how to verify and validate a simulation model. So what's verification? Verification is about building the model correctly. So here we assume that we have a conceptual model in this diagram I can show you. So here we assume that we have a conceptual model, and the conceptual model is the one that we learn in chapter 3. I mean, having the static description and dynamic description of the real system is called preparing a conceptual model. So here, and then we actually um, build an operational model which can be uh, done in Arena. I mean, in any simulation software like Arena, or you can actually code it, right? You can code it by your own, so you can prepare a program by your own. So we call that as an operational model. So verification lies here. So we want to see if we have implemented the conceptual model into the operational model correctly. Okay, and then the validation lies between the simulation model, I mean the operational model, and the real system, because in the conceptual model, and then that conceptual model transforms to uh, the simulation model, we have considered some sort of assumptions, structural assumptions, and also on the I mean for having the statistics, I mean we have assumed some sort of assumptions to have the parameters and so on. So here we will check that if all those assumptions are still valid in the simulation model in terms of the real system, and our simulation model is a real and reasonable, actually representative of the real system. So this is called validation. Okay. So in verification, we want to make sure that the simulation model is correct. So we can talk to experts. Those have knowledge and experience with the system and can judge about the system, that if the behavior of the system is like the real system. And we can use the flowcharts, and we can walk through the steps in flowchart and the program to see if everything is good. And also we can use animation. So by animating the process of the system in this simulation model, we can see again if everything is working like the real system. And so, and also we want to make sure that the computer implementation is correct. So yeah, we have a conceptual model, we have an implemented program. So we want to see if that job is done correctly. So we can use debugging, right? We can check the output. We can test the extreme and typical cases, or we can test cases with known results. And also we can use a debugging program provided. So yeah, usually for testing any uh, program, we need to consider some sort of extreme and rare situations to see how the system behaves in those extreme cases, or the cases with known results. So we know that what should be the result of this case, and we expect to have the same result by the simulation program. So by doing these steps, we can somehow verify the simulation model. And then in validation, we compare the behavior of the built simulation model with the real system. So we compare the results, and after any test, we may do some sort of adjustments and calibration in our simulation model. So we do this maybe several times in order to have the validated simulation model. So here we can do the subjective and objective tests. So we may use some experts to judge about the system's behavior, I mean the simulation model's behavior and the results, and compare the simulation model results and behavior with the real system. Or we may have data. We have data from the real system. We can enter those data in the simulation model, and we know that what was the system's behavior by those data, I mean the result, and then again we expect to have somehow the same result by the simulation model. So this is called objective test. So let's see what types of validation do we have here. The first one is phase validation. So it's somehow a qualitative method, and here we use the experts. So experts will see our simulation model, its behavior by animation, let's say, or by looking at the process and the results, and then they can judge about this uh, result, this behavior with comparing to the real system. And the second one is validation of model assumptions. So yeah, we can again use the experts to see if the structural assumptions and also the data assumptions that we have constructed in distribution fitting, those are valid somehow, or verified, or they make sense by the judgment of the expert. So these two types of validation are in the category of subjective validation, because here we are not using data and we don't have any target or objective or quantitative, let's say, analysis here, and we just use the experts' knowledge and experience to judge about the simulation model. And then we have the objective validation. So here we have validating input output transformation. So here we use historical data, I mean input and output in the real system. So we feed the input data in our simulation model, and we expect to have the results, I mean the output from the simulation model to be consistent with the output in the real system. And also we can use validation of output using a Turing test. So the last two are called somehow objective validation method, and the first two are in the category of subjective validation methods. In validation of input-output transformation, we usually increase or decrease the input data to see what's the response from the simulation model, and then we compare that response, that reaction, let's say, with the real system. And also we can change the system input or structure to test the model. So we may have some failed data for certain purpose. And so we do have this data from the real system. So we do have the input, we do have the output, and then we can feed those input data for that certain uh, uh, for that specific purpose, and then we run the simulation model with those input data, and then we can compare the responses, I mean by the simulation model and the real system, by using statistical methods to see if the results are consistent or not. Let's have an example here, the Fifth National Bank of Jasper. So this bank has two types of service, walk-in and drive-in. So, and the bank is planning to expand its drive-in service at the corner of the main street right here. Okay. So currently there is just one drive-in window, which is served by one teller. And so in order to see if the bank expands the number of tellers and windows in drive in, so what would be the impact, what would be the performance? Okay, so to do so we need to prepare a simulation model, right? So we start actually collecting data for 90 customers between 11 a.m. to 1 p.m. on Friday, which is a typical representative of typical rush hour. And so in order to estimate the interval times and service time, and so the estimated interval rate lambda equals 45 per hour, and the estimated service time is based on normal distribution with mean of 1.1 and the variance of 0.2 to the power of 2 in hours. Okay, so yeah, this is our study here. So we want to see if we have a simulation model, so how we can compare the results by the simulation model and the real system in order to verify, in order to validate the simulation model. So by having that collected data on Friday between 11 a.m. to 1 p.m., the average delay time is this 4.3 minutes. Okay, so that's the response that we have in the real system. Okay, so now assume that we have a simulation model. We have a simulation model for this system, and we have run this simulation model for 6 replications. Okay, and we do have the average delay obtained by the simulation model for 6 replications. Okay, so in order to compare the simulation model with the real system, so here let's say the real average delay time is 4.3 minutes, but for the simulation model we do have these numbers. So let's see how we can compare the simulation model with the real system. So here, if we take an average over our data, in simulation over the 6 replications, so the y bar here is the average delay time, and it's 2.51 minutes. And also we can calculate the variance, the sample variance over the data that we do have here is for 6 replications, and the standard deviation, the sample standard deviation S here becomes 0.82 minutes. Okay, so in order to compare the simulation model with the real system, here we form a hypothesis test, and the null hypothesis H0 is that the expected value of the y is 4.3 minutes. The real average that we have from the data from the real system, and H1 is the expected value is not equal to 4.3 minutes. So here we can test this hypothesis with a two-sided t-test. So here we have the test statistic t0 as y bar minus mu over s divided by square root of n. So the y bar is the average obtained from the sample data from the simulation model, and the mu is the real average from the real system. S is the standard deviation obtained again by the sample data, and n is the sample size. Okay, and if we have let's say this level of significance alpha and also the sample size n, then we can obtain the critical value by t half alpha and n minus 1 as its degrees of freedom. Okay, so yeah, this critical value can be obtained by the t distribution table that we do have, and then so yeah, we consider a significance level and a degrees of freedom which is n minus 1. Then if the t0 lies between minus t half alpha and n minus 1 and t half alpha and n minus 1, then by this we fail to reject h0. If not, if not, then we reject h0. Okay, so this is how we do the t-test analysis here. So for our example, we calculate t0 first, which becomes minus 5.34. Okay, and here the degrees of freedom becomes 5. So the critical value obtained by the t-distribution table, t half alpha 0.025 and degrees of freedom of 5 becomes 2.573. So we do have a negative and positive number. So as you see here, the minus 5.34 doesn't lie between the interval of minus 2.57 up to 2.57, right? So because of that, we reject the null hypothesis. So by this hypothesis test, we conclude that the simulation model is not validated. Okay, so because its behavior is not matching with the behavior of the real system. Okay, so that's our conclusion, and then in the next part we'll see what can we do in order to have a validated simulation model. Okay.